All right, let's look at question 3, which is an applied SN2 reaction. This is the Williamson ether synthesis. It works with an alkoxide and an alkyl halide to form the ether, as you see in part A here. Now, you can use it to form symmetrical ethers, at which point, for instance, like diethyl ether, you would have an ethyl halide and an ethyl oxide as your two reactants. But in this case, it's one that's actually unsymmetrical, which means theoretically I could do it either way, but reality is one way is usually going to be easier than the other. In this case, it's a yes-no. One possibility works, the other one does not at all. So for the one that works, since we have that designated here, it's just an SN2 reaction. The mechanism is fairly straightforward. Remember that this is just a methyl group here. So I have my alkoxide attacking that, and I have the loss of the bromide. And this, again, to remind you, is a methyl group. So that's the entire mechanism. The SN2 reaction is very simple, and when it works, it's fairly flawless. Its problem is when it doesn't work, which is the other part of this. If I went the other direction, using instead of the T-butyl side as the alkoxide, if I try to use the methyl side as the alkoxide, remember this is still a methyl group, and a T-butyl bromide, I have a problem. And that problem is that you cannot do an SN2 reaction on a tertiary carbon, like this one right here, as your leaving group. There's no law that says you can't use it as your nucleophile because it's away from the reacting site. If you look at the upper version, here's that T-butyl group, but it's very far away from the bond that's forming. This is the bond that's forming. This is way out of the way somewhere. Here, the second example, this is the bond we would be talking about forming, directly to the T-butyl group. It's not happening, not by an SN2 reaction, which is the only possibility here for substitution. So, what's going to happen instead? Well, the only thing that competes with the SN2 reaction with a strong alkoxide is using it instead of being a nucleophile as if it's a base. And at that point, we're talking about an elimination reaction. The E2 reaction will compete with the SN2 reaction if the SN2 reaction is too slow, or in this case, basically impossible. So what does that work? What does that look like? Well, each of these methyl groups has 3 hydrogens. I'm going to draw one of them for convenience here. The alkoxide will take that, and we'll get an elimination to lose the bromide. So what we'll have instead of an ether is we'll have an alkene, where this upper carbon of the alkene was this. So there's my upper carbon. That's this one. So along with that, we have basically in both cases, we have leftovers that aren't shown here. In the top case, the leftover is just the bromide ion, and it'll be balanced out by whatever the counter ion for the alkoxide is. Usually it's a sodium, so I'd have a sodium alkoxide, and I'd have sodium bromide left over as a spectator ion. We don't really care about that. In the second case, it matters, though, because it may cause other things to happen. What I mean by that is this. I only have one covalent product for the SN2 reaction in part A. There's no other covalent bonds here at all. That's not true in part B. So part B, I still have my bromide ion. And if this were a sodium alkoxide, I would still have the sodium counter ion if that's what I started with. But I have a new covalent compound here as well because there's a covalent bond formed between the alkoxide and the hydrogen. I have an alcohol. Here's my new bond from my alkoxide. So that occasionally is important. For most purposes, it's a solvent. It evaporates quickly. It's easy to get rid of. We don't worry about it. But when you're forming an alcohol, you may have some other things possible as the next reaction. We're not mixing and matching here, but just it's worth keeping in mind that opens a door to another functional group we haven't talked about yet.